Okay, physics students, today we're going to talk about the instructions for diagramming forces on an object that is sitting on an incline. And before I do that, I just want to do a short review of what do we do when we have an object sitting on a flat surface. So, a flat surface, like a tabletop or the ground, as long as the ground is level. I've got my object sitting here, and I know that gravity is always at work, and gravity, which is mass times gravity, or mass times the acceleration due to gravity, is always pulling down to the center of the earth. It's always straight down. Because that object sits on the ground, there must be something pushing up on it. We call that the normal force. Now, one thing I would like to make note of is that the word normal, in this case, does not mean unweird. Normal has another definition, and that is perpendicular. Okay, so the normal force, when we say that, we mean the perpendicular force that's pushing an object up to maintain where it is. All right, and we may have, some applied forces, might be going to the left, might be going to the right. You might have kinetic friction, you might have static friction, you might have another applied force going this way, who knows? Maybe people are fighting, whatever. But the ones that we always know that exist are the normal force and the weight. Well, what happens when we have that object, but it's not on a flat surface anymore? Let's say that we have a hill. Okay, so here's my hill, and I have my object right here, right? Now, in this situation, we know that gravity didn't turn off. Gravity still exists, but gravity, again, always goes down to the center of the earth. So it's going to go down like this. I'm going to make it a big arrow just so that we have room to write stuff. And the normal force, remember what the word normal means? It means perpendicular. So that's coming this direction. Now, they are not in direct opposition to one another as they were up here. So we know that these two forces will always be here, and on an incline they will always look like this. So what else do we know here, and what else can we figure out? Well, I know that this hill is inclined at some angle, and I'll call that theta. All right. Now here's the thing. In the flat surface example, we have an x-axis and a y-axis, which are lined up with the regular x and y axis that we're always used to. So this could be my x-axis, and this would be my y-axis. But what do we do on an incline? All right. In this situation, if we know that the motion of the object is going to be either up or down the hill, if there is any motion at all. We know that this is perpendicular to the incline, the normal force. Gravity here is sort of the odd one out. What we're going to do is we're going to take this XY axis and we're going to shift it so that it now moves or is situated right along the incline. So this is going to be my x-axis, all right? Well, my y-axis has to be perpendicular to the x-axis. So this is my new x and y-axis. Sometimes we refer to this as x prime and y prime, because what this does is it makes things easier for us. You just have to kind of get over the idea that x and y have to be the way that we've always done it. We're going to line them up with the incline. So what do I do now? Well, my normal force is right in line with y. I don't have to do anything to the normal force. But gravity, the weight, is not. And so what I'm going to have to do is I'm going to have to break this up into components, like I've done before. And we're going to call this one, because it's on the y-axis and because it's a component of FG, we're going to call this F sub GY. The x component goes right here. F sub g x. All right? So these two dotted lines, these two arrows, are components of the actual weight. Now, because they're vectors, I can take f sub gx and I'm going to move it down to here just so that I can make that right triangle. So this is fgx. So let's just talk a little bit about what these two components do. What does fgx do? Well, that's the force that's going to make an object try to slide down a hill. Okay? Fgy, this is the force that's pushing the object into the hill, which has to be counteracted by the normal force. Just like normal force and regular Fg counteracted each other. Here, the normal force is only related to the y component of the gravity, right? So, how do I determine what Fgy and Fgx are? Well, this angle here of the hill is exactly the same as this angle of this right triangle. And now I can use my trig functions because I know that f sub g is m times g. This is an equation we've used. So if fgx is the opposite side of that angle, we know that fgx is equal to fg times the sine of theta. In other words, m times g sine theta. That's important. Okay, in the y direction, y is the adjacent side now. Again, we're used to adjacent and cosine, x and cosine going together and y and sine going together. This is opposite. So this is going to be fg times the cosine of theta, or in other words, mass times gravity times the cosine of theta. All right. So these are the things that always exist when you have an object on an incline. Now, what else can you have on an incline? I could have someone pushing an object down the hill. I could have somebody trying to pull this object up the hill. I can have my applied forces wherever I want. One thing I want you to remember is that friction always opposes motion. All right? If this object is just sitting here, right, what motion does it want to have? It wants to slide down. Well, if it's just sitting there, what's holding it there? Well, in that case, it would be static friction going up the hill. What if I pull this up the hill? Well, then kinetic friction will be fighting going backward. What if it's sliding down the hill? Kinetic friction will be going uphill that time. So let me go through a few different examples here. And this is actually your homework assignment today, but I will go over this just so you can check and kind of see how you're doing. So I've got 12 different scenarios here, and I'm going to diagram and write the force equations for all of these. So the first one is kind of where we just were, an object at rest on an incline. So here's my object at rest. It's on an incline, some angle theta. And what forces do I have? Well, I always have F sub g, which equals m times g. I always have my normal force. And I need to write out those component forces, F, G, Y, and F, G, X. Now, this object is not accelerating, it's just sitting there, which means that because there's this X force trying to bring it down, I'll draw it up here, FGX, because that force is trying to accelerate it downward, there must be a force holding it back. And because it's not moving, that would be called static friction. So let's write the force equations here. First of all, I know that it's at rest, so A equals 0, which means that the net force equals 0, and that's for both directions. So the sum of the forces in the x direction will be Fgx, and you might say, well, wait, that's going downhill, shouldn't that be negative? I typically always set things up so that friction is going to be negative, in my preference. Fgx minus Fs equals max, which again is 0. In the y direction, I have Fn and Fgy. So here I've got the normal force minus Fgy equals may. And again, we said A is 0, so these are my force equations. Now, one thing that happens a lot is I get people who say, well, what about F sub g here? What about this force? Why doesn't that count? It does. It counts in the sense that I have Fgx here and Fgy there. That's where it comes from. All right, moving right along. Objects held at rest on an incline by a rope. Okay, so now, here's my incline. Here's weight coming straight down. There's a rope, maybe it's tied to a tree or something, holding this on the hill here, right? There may also be some static friction holding it there. I don't know, there might be, there probably is. And then I've got my normal force. I've got Fgx and Fgy, right? So in the x direction, I have Fgx, and then I'm going to subtract, oh, that should just be F applied, the rope force and the static friction force. That equals max, which is 0. In the y direction, we're going to see this a lot. It's basically going to be the same every time. Fn minus Fgy equals may, and that's 0. Okay. All right, moving right along. Next one, we have an object sliding down an incline with friction at a constant speed. All right, so what forces do we have here? We have Fg and Fn. Again, start with those all the time because you always know they're there. Know that we have Fgx trying to bring it down the hill, and we have Fgy bringing it into the surface of the hill. All right, and it says there is friction, so friction is going backwards here. That's going to be Fk. And it tells us that it's moving at a constant speed, which means that A equals 0, and therefore the net force is equal to 0 as well. And again, that's for both directions. So the sum of the forces in the x direction will be Fgx minus Fk equals max, or 0. In the y direction, it's going to be Fn minus Fgy equals may equals 0. Notice that this one has been the same every single time. All right. Next, an object sliding down an incline with no friction at an increasing speed. So now acceleration is not 0. All right. And there is no friction. So let's draw that. Okay, so it's moving down, but some things always apply. There's always weight. There's always a normal force. And why do things go down the hill? There's no force making that go down. Well, you already know that, yes, there is. And it's the x component of the weight that makes it happen. All right? And so in the x direction, I only have one force because there's no friction, and that's Fgx. And it says there is acceleration, so that's ma sub x, and that's my x equation. In the y direction, guess what? Same thing. Fn minus Fgy equals may, which is 0. All right, next one. An object sliding down an incline with friction at an increasing speed. Okay, so Got a few things going on here, but like I said, we always have weight, we always have normal force. Now, there will be a kinetic friction force pulling back because it's moving. There will be the x component of weight and the y component of weight. And so we go the sum of the forces in the x direction, Fgx minus Fk equals max, and it says it is increasing its speed, so I can't cancel that out. In the y direction, Fn minus Fgy. And again, no acceleration in the y direction. So that's different from this one up here where there was friction and it was moving, but at a constant speed, the sum of the forces was 0. Here it's not 0, it's max. It's got some acceleration that we don't know. All right, next one, object being pulled up an incline at a constant speed with no friction. All right, so what's going on here? Let's draw our object. Got our weight, got our normal force. All right, being pulled up the incline, so there's some applied force here. And we also have Fgx, and we have Fgy. Those things, Fgx and Fgy, are there every time as well. It says it's a constant speed, so A equals 0, and there's no friction. Sum of the forces must also equal 0 if A is 0. So we go sigma Fx equals, now I'm going to say that because it's going up the hill, I'm going to choose F applied to be my positive direction. Subtract Fgx, which is kind of fighting that, equals max, which is 0. And you know what sigma Fy is. All right, moving right along, 6 more. All right, first one here, an object being pulled up an incline at a constant speed with friction. All right, so we're just making each of these a little bit more complicated than they were before. So I still have gravity, normal force, Fgx, Fgy, but it's being pulled up. This is my applied force. But it says there is friction now, and so friction always applies the direction of motion. So friction will be going downhill this time. So in the x direction, it says constant speed still, so A equals 0, sum of the forces equals 0. So in the x direction, I have applied, F applied force, minus Fgx minus Fk equals max, which is 0. And for as complicated as we try to make this, the y direction remains the same. All right, next one. An object is being pushed down an incline with friction at a constant speed. So start out the same way, Fg, Fn, Fgy, Fgx. Now it's being pushed down the hill, so there's an applied force going in the same direction downhill. And there is friction, and friction again opposes motion, so that's got to be going uphill. A is 0 because it's a constant speed, which means the sum of the forces is also 0. So I go sigma Fx equals F applied plus Fgx minus Fk. And again, I set this up so that friction is going to be negative. Equals max, which is 0 again because there is no acceleration. Y direction, same. All right, moving right along. Object being pushed down an incline with no friction but is accelerating. Fg, F sub n, Fgx, Fgy, F applied pushing it down. There's no friction. And so now I'm going to go sigma Fx equals F applied plus Fgx equals max. And it's not 0, so I leave that there. no change in f sub y. All right, now being pushed down an incline with friction and is accelerating. So kind of combine the last two that we had. So here we start with our things that we always have. Now, there is friction, so that's going to be going backward because it's moving downward, and it's being pushed down the hill, so that's F applied. So, I'm getting a little wavy with my handwriting here. All right, so Fx, we have Fgx plus F applied minus F sub k equals MAX. There is acceleration, so we can't cancel that out. In the y direction, we have what we always have. All right, two more. An object sliding up an incline with no applied force and no friction. And you might say, well, how is an object going to slide up a ramp? Well, you can give it a push and let go, and it's going to slide up until it comes to a stop, right? It's not going to stop immediately. So it's moving up the ramp. There is no applied force, and there is no friction. But there's always gravity, and there's always a normal force, and there's always the x component of gravity, and there's always the y component of gravity. All right. There is no friction, and there's no applied force. This is all we have. So the motion is this way, which I'm going to call our positive direction, which means that when I sum up these forces, there is no force going in that direction. I do have a force going backwards, so that has to be negative Fgx equals MAX. Why is it important to make this negative? That'll give me a negative acceleration, which means that the object is going to slow down going in that direction, which it obviously will. It's going to slow down until it comes to a stop, and then it's going to go back down. It's not really important what you call positive and negative as long as you stay consistent throughout a problem or set of problems related to the same situation. All right, FGY, guess what? No change. And finally, we have an object sliding up an incline with no applied force, but there is friction. So in this situation, again, it's moving this way. So we have F sub g, F sub n, Fgx, Fgy, and friction going down. Because friction always opposes the motion because the motion is going uphill. So I should make this a little longer. There we go. All right, so in the x direction we have negative Fgx minus Fk equals MAX. And in the y direction we have the same thing as usual. All right, there you go.